What specific problem does the new method or algorithm aim to solve?
The new method or algorithm, test time training (TTT), aims to address the issue of traditional machine learning models that are trained on shuffled datasets with ID instances which do not reflect how human learning occurs. TTT introduces a novel approach where each test instance defines its own learning problem, allowing the model to be optimized for each specific test instance. This inner-loop learning paradigm enables the model to learn from potentially very long sequences with strong temporal dependencies, where any piece of data can be used for both training and testing. By formulating an explicit learning problem for each test instance, TTT shifts the focus towards learning at test time, which is more aligned with how human intelligence operates. This approach provides a more promising connection with human learning processes, making the model more adaptable and effective in real-world scenarios.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method, test time training (TTT), works by formulating a learning problem for each test instance, where the test instance itself defines the target of generalization. The core idea is to train a model specifically on the test instance using a self-supervised task, rather than using a predictor optimized for all training instances on average. The learning problem is defined by the test instance, and a model f_x is trained on this specific instance, often with an initialization from a general model f. The model f_x is then used to predict the output for the test instance. This process allows for more tailored and effective learning on individual test instances. The update rule in TTT involves an explicit step of optimization, where the model is updated based on the self-supervised loss calculated for the test instance. The outer loop parameters are optimized alongside the inner loop weights, allowing for efficient learning at test time. The method also incorporates mini-batch training and a dual-form optimization to improve hardware efficiency and speed. Overall, TTT provides a new perspective on learning at test time, enabling more adaptive and effective modeling for individual instances.
What are the theoretical or practical benefits of using this method?
The theoretical benefits of using the test time training (TTT) method, outlined in the paper, include the ability to formulate a learning problem specific to each test instance, allowing for targeted optimization for individual instances. This approach contrasts with traditional machine learning methods that optimize for all training instances on average. TTT also introduces the concept of learning at test time, where each test instance defines its own generalization problem, leading to potentially improved performance, especially on outliers. Additionally, TTT enables the use of self-supervised tasks for formulating learning problems, providing flexibility and adaptability in training models. On a practical level, TTT offers the advantage of efficient hardware utilization through concepts like mini-batch TTT and the dual form, which optimize the update rule for faster computation. The method also allows for parallelization of certain computations, leading to improved efficiency in wall clock time during training and inference. Furthermore, TTT layers can be integrated into existing network architectures, providing a practical building block for large language models. Overall, TTT presents a novel approach to sequence modeling that combines the benefits of self-supervised learning, efficient hardware utilization, and targeted optimization for individual test instances, offering both theoretical insights and practical advantages in training and deploying models.
How is the method validated or tested?
The method is validated or tested through a series of experiments comparing TTT linear and TTT MLP with two baselines, Transformer and Mamba, across different model sizes and context lengths. The experiments are conducted on datasets like the Pile and Books 3, with context lengths ranging from 2K to 32K. The evaluation protocols strictly follow those outlined in the Mamba paper to ensure fairness. The experiments include training models from scratch, as well as fine-tuning transformers on longer contexts. The performance of the models is evaluated based on perplexity metrics, and the results are presented in figures and tables. The experiments also explore the impact of different backbone architectures on the performance of TTT layers. Additionally, the wall clock time efficiency of the models is evaluated, comparing the latency for forward and generate operations on TPUs and GPUs. The experiments aim to showcase the advantages of TTT layers in handling long contexts and larger models, demonstrating their potential in improving language modeling tasks.
What results were achieved with this new method?
The new method, Test Time Training (TTT), achieved significant results in the study. TTT layers, specifically TTT linear and TTT MLP, outperformed the modern RNN Mamba in evaluations ranging from 125 m to 1. 3B parameters. TTT linear was shown to be faster than the Transformer at 8K context and matched Mamba in terms of performance. The study demonstrated that TTT layers can take advantage of their larger hidden states to compress more information in long contexts, leading to improved performance over existing RNNs. Additionally, TTT layers showed a widening advantage over Mamba as the context length grew longer, indicating their effectiveness in handling longer sequences. The method also introduced practical innovations to improve efficiency in wall clock time, such as mini-batch TTT and the dual form, which made TTT linear already a practical building block for large language models, LLMs. Overall, the results showcased the potential of TTT layers as a promising approach for sequence modeling, offering improved performance and efficiency compared to existing RNNs and transformers.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method outlined in the paper include the lack of a clean linear fit in the log-log plot of flops versus perplexity, which makes it challenging to derive an empirical scaling law. Additionally, the method does not cleanly fit a linear scaling trend even for the transformer baseline, which can hinder the ability to predict performance based on computational resources. Another limitation is the difficulty in training with millions or billions in context length, which would require larger models, according to the findings in the paper. Furthermore, the method may face challenges in more ambitious instantiations of the inner loop model F, especially when dealing with video tasks or embodied agents that require larger and more complex models. Additionally, the method's reliance on self-supervised learning for compression heuristic may limit its performance in scenarios where handcrafted tasks or priors could be more effective. Lastly, the method's reliance on mini-batch TTT and the dual form for systems optimization may introduce complexities in implementation and optimization, which could impact its scalability and efficiency in real-world applications.